Preparing for a generative AI engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How is a large language model different from a traditional machine learning model? A traditional ML model is usually trained for one supervised task, like fraud detection or churn prediction. An LLM is pre-trained on massive text corpora using self-supervised objectives, then adapted through prompting, fine-tuning, or alignment. The key difference is generalization. LLMs learn language patterns, reasoning traces, and world knowledge that transfer across tasks. In production, I still treat them as probabilistic systems that need evaluation, guardrails, and monitoring. While answering, focus on pre-training, scale, self-supervised learning, contextual generation, transfer learning, and why LLMs can perform many tasks without task-specific training. Question 2. What happens during the pre-training phase of a transformer-based LLM? Pre-training teaches the model general language capability before any application-specific tuning. Text is tokenized, passed through transformer layers, and the model learns to predict missing or next tokens by minimizing loss across huge datasets. This requires distributed training, GPUs or TPUs, careful data filtering, and stability techniques. The output is not a chatbot yet. It is a base model with broad statistical knowledge that can later be instruction-tuned or fine-tuned. Make sure to cover tokenization, next token prediction, or masked modeling, transformer architecture, large-scale datasets, optimization, and why pre-training is expensive but broadly reusable. Question 3. Explain the transformer architecture and why it became dominant in generative AI. Transformers became dominant because self-attention lets every token interact with every other token efficiently. Unlike RNNs, they process sequences in parallel, which makes training on massive corpora practical. Positional encodings preserve order, while multi-head attention captures different relationships in the text. Decoder-only transformers power many LLMs because they are excellent at next token generation. The trade-off is attention cost, which grows with context length. In your answer, talk about self-attention, positional encoding, parallelization, long-range dependencies, encoder versus decoder usage, and the scalability advantage over recurrent models. Question 4. What is tokenization, and why does it matter in LLM applications? Tokenization is the conversion of text into model-readable units, often subwords rather than full words. It matters because models do not see raw characters. They operate on token IDs. Token count affects context length, latency, and API cost. For example, rare words, code, or non-English text may split into more tokens. When building applications, I budget tokens carefully for system instructions, retrieved context, user input, and expected output. Be sure to mention subword tokens, vocabulary, context window limits, cost calculation, multilingual behavior, prompt length, and how tokenization affects latency and output quality. Question 5. What is prompt engineering, and how do you design a reliable prompt? Prompt engineering is the practice of structuring instructions in context so the model produces consistent, useful output. I start with a clear role, define the task, include constraints, and specify the output format. For harder tasks, I add examples and separate reference data from instructions. I also test adversarial and ambiguous inputs. A strong prompt is not magic. It is an interface contract between the application and a probabilistic model. While answering, cover role instructions, task clarity, examples, constraints, output schemas, context ordering, ambiguity reduction, and iterative testing across edge cases. Question 6. When would you use fine-tuning instead of prompt engineering? I use prompt engineering first because it is cheaper, faster, and easier to iterate. Fine-tuning makes sense when I need consistent style, domain-specific behavior, reduced prompt length, or repeated task patterns that examples cannot reliably enforce. It requires high-quality training data, validation sets, and regression testing. I would not fine-tune just to inject changing facts. Retrieval is better for that. Fine-tuning changes behavior, while RAG supplies knowledge. Make sure to compare cost, latency, behavior consistency, domain adaptation, data requirements, maintenance burden, and cases where prompting or retrieval is sufficient. Question 7. What is Retrieval-Augmented Generation, and how would you build a RAG pipeline? RAG combines search with generation so the model answers using external knowledge. I ingest documents, clean them, split them into chunks, create embeddings, and store them in a vector database. At query time, I embed the user question, retrieve relevant chunks, optionally re-rank them, and pass them to the LLM with instructions. This reduces hallucination and keeps knowledge fresh, but quality depends heavily on chunking, retrieval accuracy, and evaluation. In your answer, include document ingestion, chunking, embeddings, vector search, re-ranking, prompt assembly, citation handling, evaluation, and hallucination reduction. Question 8. How do embeddings work, and where are they used in generative AI systems? Embeddings map text, images, or other inputs into dense vectors where semantic similarity becomes measurable. If two sentences have similar meaning, their vectors should be close under cosine similarity or dot product. In Gen AI systems, I use embeddings for semantic search, RAG retrieval, recommendations, clustering, and duplicate detection. They are powerful but not perfect. They can miss exact constraints, inherit bias, and require careful model selection for the domain. Be sure to cover dense vector representations, semantic similarity, vector databases, cosine similarity, clustering, retrieval, recommendation, deduplication, and limitations around meaning and bias. Question 9. How would you evaluate the quality of an LLM application? I evaluate an LLM application at multiple levels. First, I create a representative test set with expected behaviors, edge cases, and failure examples. Then I measure task metrics like accuracy, groundedness, citation correctness, toxicity, latency, and cost. Human review is important for subjective tasks. In production, I monitor drift, user feedback, retrieval quality, and regression after prompt or model changes. Evaluation must match the business risk, not just benchmark scores. While answering, discuss offline test sets, human review, task-specific metrics, hallucination rate, groundedness, latency, cost, safety, regression testing, and production monitoring. Question 10. What are hallucinations in LLMs and how do you reduce them? Hallucination is when a model produces plausible but false or unsupported information. It happens because the model predicts likely text, not verified truth. I reduce it by grounding answers in retrieved documents, forcing citations, limiting the answer to provided context, and adding refusal instructions when evidence is missing. For high-risk domains, I add human review or deterministic checks. The goal is not zero hallucination everywhere, but controlled risk for the use case. Make sure to mention probabilistic generation, lack of grounding, retrieval, constrained decoding, refusal behavior, source citations, confidence handling, and evaluation against factual datasets. Question 11. How do you design a production-ready LLM API service? A production LLM service should be treated like any critical backend, plus model-specific controls. I validate inputs, use versioned prompt templates, abstract model providers, and enforce timeouts, retries, and rate limits. I log structured metadata, not sensitive raw data, and track latency, token usage, failures, and quality signals. For resilience, I add caching, fallbacks, and graceful degradation. Streaming improves UX, but I still need cancellation and safety checks. In your answer, talk about request validation, prompt templates, model abstraction, retries, timeouts, streaming, caching, rate limits, observability, security, and fallback strategies. Question 12. What is instruction tuning, and how is it different from RLHF? Instruction tuning trains a base model on examples of instructions and ideal responses, so it learns to follow user requests. RLHF goes further by using human preference comparisons to train a reward model, then optimizing the LLM toward preferred behavior. Instruction tuning teaches task format and helpfulness directly. RLHF improves alignment with human preferences, such as being safer or more concise. Both convert a raw language model into a better assistant. Be sure to explain supervised instruction response datasets, alignment, human preference data, reward models, reinforcement learning, and why both improve user-facing behavior. Question 13. How would you handle sensitive data and privacy in a generative AI application? I start by minimizing what data reaches the model. Sensitive fields should be detected, redacted, masked, or tokenized before prompts are built. I enforce encryption, access control, audit logging, and strict retention policies. If using third-party APIs, I verify training usage, data residency, and compliance terms. Prompt and output logs need special care because they may contain PII. Privacy is an architecture concern, not a final filter. While answering, cover PII detection, redaction, encryption, access controls, data retention, vendor policies, audit logging, prompt leakage, compliance, and least privilege design. Question 14. What are common security risks in LLM applications? The biggest LLM security risks come from treating model output as trusted. Prompt injection can override instructions, especially when retrieved documents or web pages contain malicious text. Tool-using agents may leak data, call unsafe APIs, or perform unintended actions. I mitigate this with input isolation, least privilege tools, allow lists, approval gates, sandboxing, and output validation. The model should recommend actions, but deterministic systems should enforce security boundaries. Make sure to cover prompt injection, data exfiltration, tool misuse, insecure plugins, jailbreaking, indirect prompt injection, output trust, sandboxing, and allow listed actions. Question 15. How do you choose between open source models and proprietary LLM APIs? I choose based on constraints, not ideology. Proprietary APIs usually provide strong quality, fast iteration, managed scaling, and tool ecosystems. Open source models give more control over privacy, deployment, cost at scale, and customization. The trade-off is operational complexity. Hosting, optimization, monitoring, and model upgrades become my responsibility. For a prototype, I may start with an API. For regulated data or predictable high volume, self-hosting can be compelling. In your answer, compare quality, latency, cost, deployment control, privacy, customization, infrastructure effort, vendor lock-in, compliance, and long-term maintenance. Question 16. What techniques can reduce latency and cost in an LLM-powered product? Cost and latency usually come from token volume, model size, and repeated calls. I reduce them by shortening prompts, caching common responses, using smaller models for simple tasks, and routing only hard requests to larger models. Streaming improves perceived latency, while batching helps back-end throughput. For self-hosted models, quantization and optimized inference engines matter. I also avoid stuffing irrelevant context into prompts, because every token costs money and attention. Be sure to mention smaller models, prompt compression, caching, streaming, batching, model routing, quantization, retrieval optimization, token budgeting, and asynchronous workflows. Question 17. How would you build an AI agent that can use external tools safely? An agent becomes useful when it can call tools, so increases risk. I define strict tool schemas, validate arguments, and give the model only the permissions needed for the task. Dangerous actions like payments, deletes, or emails should require confirmation. I separate reasoning from execution, log every tool call, and handle failures deterministically. The agent can decide what to request, but the application controls what is actually executed. While answering, discuss tool schemas, planning, function calling, permissions, validation, execution sandboxing, human confirmation, state management, observability, and failure recovery. Question 18. What is model quantization, and why is it useful for LLM deployment? Quantization reduces the numerical precision of model weights, for example from FP16 to INT8 or INT4. This lowers memory usage and can speed up inference, making larger models fit on limited GPUs or edge devices. The trade-off is possible quality loss, especially on reasoning or domain-specific tasks. I validate quantized models against real evaluation sets, not just generic benchmarks. It is a deployment optimization, not a replacement for model quality. Make sure to cover reduced precision, memory savings, faster inference, GPU constraints, accuracy trade-offs, post-training quantization, quantization-aware training, and edge deployment. Question 19. How do you monitor an LLM application after it goes live? Monitoring needs both engineering and quality signals. I track latency, error rates, token usage, provider failures, cache hit rate, and cost per request. For model quality, I sample conversations, collect user feedback, monitor safety violations, and evaluate retrieved context relevance. Every prompt and model version should be traceable. When quality drops, I need to know whether the cause is data drift, retrieval failure, prompt change, or model provider behavior. In your answer, include latency, token usage, cost, errors, user feedback, quality sampling, safety violations, retrieval metrics, drift, prompt versions, and incident response. Question 20. How would you design a customer support chatbot using generative AI? I would design it as a grounded assistant, not a free-form chatbot. The bot authenticates the user when needed, retrieves relevant policy or account information, and answers only from approved sources. It should handle common intents, ask clarifying questions, and escalate to a human when confidence is low or the case is sensitive. I would monitor containment rate, satisfaction, hallucinations, and escalation quality. Good support bots prioritize trust over cleverness. Be sure to cover intent handling, RAG over support docs, escalation, user authentication, conversation memory, guardrails, evaluation, analytics, multilingual support, and fallback paths. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.